Tonight, we embark on a journey that will stretch the limits of our imagination, pushing against the boundaries of what our minds can truly grasp. We're going to confront a question that seems, on the surface, almost childish in its simplicity. How many stars exist in the universe? You've probably looked up at the night sky countless times, perhaps on a clear, moonless evening far from city lights, and felt a sense of awe at the sparkling expanse above. You've seen the countless pinpricks of light, each one a distant sun, and wondered about their number. But here's the profound truth. What you see with your naked eye is merely the barest whisper of the cosmic reality. The true answer to our question is so staggeringly immense, so far beyond our everyday experience, that it fundamentally alters our perception of existence itself. It changes how we see our place, our planet, and the very fabric of the cosmos. It's a number that defies intuitive understanding, yet it's a number we can, through the power of science and observation, estimate with remarkable precision. This journey will take us from the familiar comforts of our own backyard, gazing at the stars we can touch with our eyes, to the farthest reaches of the observable universe, peering back in time to the very dawn of creation. We will move through scales of distance and numbers that challenge our cognitive abilities, always striving to paint a vivid picture of the unfathomable abundance that surrounds us. By the end of this exploration, you're going to understand not just the number itself, but the incredible scientific detective work that went into arriving at it, and the profound implications it holds for humanity. Before we dive into the depths of cosmic illumination, if you find this kind of deep exploration of the universe as fun, it's a small thing for you, but it makes a huge difference for me. Now, let's begin our count. Our local view, counting stars in the night sky. Let's begin our quest for the universe's stars, with the most immediate and personal perspective, what we can see with our own eyes. Imagine yourself under a perfectly dark, clear sky, far from any light pollution. Perhaps you're camping in a remote desert, or sailing far out at sea. You look up, and the sky is a glittering canopy, seemingly packed with countless stars. This is often the starting point for our cosmic wonder, this immediate, visceral experience of the night sky. But how many stars are actually visible to the naked eye? The answer might surprise you, and it's far, far smaller than the true number of stars in the universe. Under ideal conditions, an observer with excellent eyesight, in a location with absolutely no light pollution and a perfectly clear atmosphere, might be able to see around 2,500 stars at any given moment, from a single hemisphere. If you consider the entire celestial sphere, meaning if you could see both hemispheres simultaneously, which is impossible from one spot on Earth, the total number of stars bright enough to be seen without optical aid is roughly 9,000. That's it. 9,000. This number, while seemingly large when you're straining your eyes to pick out individual points of light, is actually incredibly tiny in the grand scheme of things. It's less than 1/10,000,000th of a single % of the stars in our own galaxy, the Milky Way, let alone the entire universe. Why is this number so small? There are several key factors at play, all conspiring to limit our direct visual access to the cosmos. The first, and perhaps most significant in our modern world, is light pollution. The glow from cities, towns, streetlights, and buildings scatters in the atmosphere, creating a diffuse light that washes out the fainter stars. Even a small amount of light pollution can reduce the visible star count dramatically. In a typical suburban area, you might only see a few hundred stars. In a brightly lit city center, you might be lucky to see a dozen or so of the very brightest stars, perhaps Venus or Jupiter if they are visible. But the vast majority are simply obliterated by the artificial glow. Beyond light pollution, our own atmosphere plays a role. Even on a perfectly clear night in a remote location, the Earth's atmosphere acts as a filter. It scatters light, absorbs some wavelengths, and causes stars to twinkle, which can make them harder to perceive. Dust, aerosols, and water vapor, even in small amounts, can diminish the clarity of our view. This is why observatories are often built on high mountains, above a significant portion of the atmosphere, or even better, launched into space, like the Hubble and James Webb Space Telescopes, where the atmosphere is no longer a hindrance. Then there's the limitation of human vision itself. Our eyes are remarkable instruments, capable of detecting single photons under certain conditions, but they have a finite sensitivity. Stars that are too faint, either because they are intrinsically dim or because they are incredibly far away, simply don't send enough photons to our retinas to register as a discernible point of light. Our eyes also have a limited field of view and resolution. Even if a star is bright enough, if it's too close to another star, our eyes might perceive them as a single, slightly brighter point rather than two distinct stars. The illusion of a crowded sky, therefore, is just that, an illusion. What we perceive as an uncountable multitude is, in fact, a very small, select group of the closest and brightest stars. The vast majority of stars, even in our own immediate galactic neighborhood, are simply too faint or too far to be seen without optical aid. This realization is the first step in understanding the true scale of stellar abundance. Our naked eye view, while inspiring, is profoundly misleading when it comes to the sheer numbers involved. Early attempts by ancient astronomers to count stars were, understandably, limited by these factors. Without telescopes, they could only catalogue what was visible. Figures like Hipparchus and Ptolemy meticulously charted thousands of stars, creating constellations and laying the groundwork for astronomy. Their catalogues were impressive achievements for their time, but they represented only the brightest beacons in the night. They had no way of knowing about the billions upon billions of fainter, more distant stars that lay hidden beyond the reach of human perception. Their universe, as perceived from Earth, was a relatively small, enclosed sphere, with stars fixed upon it. The invention of the telescope in the early 17th century by figures like Hans Lippershey and Galileo Galilei was a revolutionary moment. For the first time, humanity could extend its vision beyond the natural limits of the eye. When Galileo pointed his crude telescope towards the Milky Way, he didn't just see a hazy band of light, he resolved it into countless individual stars, far too many to count. This was the first hint that the number of stars was far greater than anyone had previously imagined, a number that stretched beyond thousands into the realm of hundreds of thousands, and eventually, millions. The telescope didn't just make distant objects appear closer, it revealed a universe teeming with previously unseen stellar abundance, shattering the ancient cosmological models and opening up a new, vastly larger cosmos for exploration. This profound shift in perspective, from a few thousand visible stars to an unimaginable multitude, is just the beginning of our journey into the true number of stars. Zooming in, our Sun and its immediate neighborhood. To truly appreciate the countless stars of the universe, we must first understand our own star, the Sun, and its place in the cosmic scheme. Our Sun, that brilliant orb that warms our planet and fuels all life, is, in essence, just another star. It might feel unique and central to us, and indeed it is for our solar system, but from a galactic perspective, it is remarkably ordinary. It's a yellow dwarf star of average size and brightness, comfortably nestled in the main sequence phase of its life, steadily fusing hydrogen into helium in its core. There's nothing particularly special or unusual about our Sun, compared to the hundreds of billions of other stars in the Milky Way. This ordinariness is, in itself, a profound realization, hinting at the sheer abundance of similar stellar systems throughout the cosmos. Our solar system, a collection of planets, moons, asteroids, and comets orbiting our Sun, is also, as far as we can tell, a fairly typical stellar system. We know now that planets are incredibly common on other stars. The discovery of thousands of exoplanets over the past few decades has shown us that planetary formation is a natural outcome of star formation. So, when we think about the Sun, we're not just thinking about a single star, but often a star that likely hosts its own retinue of worlds, just like ours. This multiplies the cosmic count, not just of stars, but of potential homes for life. But how close are the other stars? If our sun is just one among many, how far do we have to travel to find the next one? The answer, even to our nearest stellar neighbors, is staggering, measured in light years, a concept we've explored previously as a unit of cosmic distance. The closest star to our Sun is Proxima Centauri, a small, dim red dwarf star. It's part of a triple star system called Alpha Centauri, which also includes Alpha Centauri A and B. To Sun-like stars locked in a gravitational dance, Proxima Centauri is approximately 4.24 light-years away from us. To put that in perspective, if you could travel at the speed of the fastest spacecraft humans have ever built, the Parker Solar Probe, which reaches speeds of up to 192 kilometers per second when close to the Sun, it would still take you about 6,800 years to reach Proxima Centauri. That's longer than the entire span of recorded human history. It's a journey that would span hundreds of human generations, a testament to the vast emptiness that exists even between the closest of stars. This immense distance highlights the fact that even in our immediate cosmic neighborhood, space is predominantly void. Stars are tiny, luminous islands scattered across an ocean of nearly perfect vacuum. The Alpha Centauri system, including Proxima Centauri, is not an anomaly. Our local bubble of space is dotted with other stars, though they are much farther than Alpha Centauri. Barnard's star, another red dwarf, is the second closest star system to our Sun, at a distance of about 5.9 light-years. WOLF 359, also a red dwarf, is 7.9 light-years away. Sirius, the brightest star in our night sky, a binary system consisting of a bright white main sequence star and a white dwarf companion, is 8.6 light-years distant. Within about 20 light-years of Earth, there are approximately 130 known star systems, many of which are binary or triple star systems, meaning they contain 2 or 3 stars orbiting each other. This density of stars in our local bubble, while seemingly sparse from a human perspective, gives us a microcosm of what to expect on a larger scale. Red dwarfs, like Proxima Centauri, Barnard's star, and Wolf 359, are the most common type of star in the galaxy, making up about 70% of all stars. They are small, dim, and long-lived, often shining for trillions of years. Despite their abundance, none of them are visible to the naked eye due to their low luminosity. This tells us something crucial. The stars we can see are not representative of the majority. The night sky, even without light pollution, overwhelmingly presents us with the larger, brighter, but less common stars. The true stellar population is dominated by these faint, ubiquitous red dwarfs. The vast emptiness between these nearby stars, even at distances of only a few light-years, serves as a powerful reminder of the sheer volume of space. If you could somehow travel to Proxima Centauri, our Sun would appear as just another bright star in the sky, blending in with countless others. Our entire solar system would be compressed into an invisible speck around it. This perspective begins to dissolve our anthropocentric view, placing our Sun and our world within a larger, more abundant, and profoundly vast cosmic context. The lesson from our immediate neighborhood is clear. Stars are numerous, but space is even more so. The true count of stars will emerge not from our immediate surroundings, but from the immense structures they form. Galaxies, the Milky Way, our galactic home, having established the limitations of our naked eye, and the vastness of even our local stellar neighborhood, it's time to zoom out further, to the majestic structure that contains our Sun and billions of its companions, the Milky Way galaxy. The concept of a galaxy as an island universe was revolutionary. For much of human history, the hazy band of light we call the Milky Way was thought to be the entire universe, with all other visible stars contained within it. It wasn't until the early 20th century that Edwin Hubble's observations unequivocally proved that other spiral nebulae were, in fact, distant galaxies, immense star systems far beyond our own. This discovery expanded our understanding of the cosmos by an unimaginable degree, transforming our universe from a single galaxy into a vast ocean of galaxies. each containing billions or even trillions of stars. Our Milky Way is a barred spiral galaxy, a magnificent pinwheel of stars, gas, and dust, spanning an estimated 100,000 light-years across. It possesses a complex and beautiful structure. At its heart lies a central bulge, a dense, football-shaped region packed with older stars. This bulge is home to a supermassive black hole, Sagittarius A, which has a mass equivalent to about 4.3 million suns. Surrounding the bulge is a flat disk, composed of several spiral arms, where most of the galaxy's gas, dust, and younger, hotter stars reside. Our Sun is located in one of these spiral arms, the Orion Arm, about 26,000 light-years from the galactic center. Encasing the entire disk and bulge is a diffuse halo, a spherical region containing globular clusters, dense collections of hundreds of thousands of very old stars, isolated stars, and a vast amount of invisible dark matter, which dominates the galaxy's mass and gravitational pull. Estimating the number of stars within the Milky Way is a formidable challenge, akin to trying to count trees while standing in the middle of an enormous, foggy forest. We are inside the galaxy, meaning much of it is obscured from our view by thick clouds of interstellar dust and gas. These dust lanes absorb and scatter visible light, making it impossible to see through them to the far side of the galactic disk, or even to the very center. Imagine trying to count cars in a massive traffic jam, when you can only see a few feet in front of you due to heavy fog. Astronomers employ several ingenious methods to overcome these obstacles and arrive at an estimate. One approach involves studying the galaxy's rotation. By observing how stars and gas clouds orbit the galactic center, astronomers can infer the total mass of the galaxy, including both visible matter stars, gas, dust and invisible dark matter. Once the total mass is estimated, and after accounting for the mass of gas and dust, they can divide the remaining stellar mass by the average mass of a star, which is primarily determined by the prevalence of red dwarfs, to get an approximate star count. Another method involves carefully counting stars in specific, unobscured regions of the galaxy, and then extrapolating that density to the entire galactic volume. Telescopes like the Gaia spacecraft, operated by the European Space Agency, are revolutionizing this process. Gaia is meticulously mapping the positions, distances, and motions of over 1 billion stars in our galaxy with unprecedented precision. While 1 billion stars is only a fraction of the Milky Way's total, this data allows astronomers to build a much more accurate three-dimensional model of the galaxy's structure and stellar density, leading to better overall estimates. Through these methods, the current best estimates for the number of stars in the Milky Way galaxy range from 100 billion to 400 billion stars. This is a vast range, reflecting the inherent difficulties in such a grand calculation. But even the lower estimate of 100 billion is a number that strains our comprehension. It's 100,000 million stars, each one a sun, many with their own planetary systems. Our Sun is just one of these hundreds of billions, a tiny speck in a colossal cosmic dance. The stellar population of the Milky Way is incredibly diverse. While red dwarfs are the most common, the galaxy is also home to massive, brilliant blue giants that burn hot and fast, living for only a few million years before exploding as supernovae. There are yellow dwarfs like our Sun, stable for billions of years. There are red giants and supergiants, stars that have expanded enormously as they near the end of their lives. And there are the stellar remnants, white dwarfs, the dense, Earth-sized cores of dead stars, neutron stars, incredibly compact objects formed from the collapse of massive stars and stellar mass black holes, regions of space-time where gravity is so intense that nothing, not even light, can escape. Each of these different types of stars contributes to the overall mass and luminosity of the galaxy, and each represents a different stage in the grand cycle of stellar evolution that has been unfolding for billions of years within the Milky Way. The Milky Way is not a static entity, it's a dynamic, living system. Stars are constantly being born in vast stellar nurseries, clouds of gas and dust where gravity pulls matter together to form new suns. Old stars are dying, some gently fading away as white dwarfs, others spectacularly exploding as supernovae, enriching the interstellar medium with heavier elements that will eventually form new stars, planets, and even life. Our Sun, along with its planets, orbits the galactic center at a speed of about 230 kilometers per second. Even at this incredible speed, it takes our solar system about 225 million to 250 million years to complete one full revolution around the galaxy. The last time the Sun was in its current position in the galaxy, dinosaurs were just beginning to evolve on Earth. This immense galactic year underscores the deep cosmic timescales involved in the life of a galaxy. The Milky Way, with its hundreds of billions of stars, is just one of many such magnificent structures in the universe, and we're now ready to look beyond its familiar boundaries, beyond our galaxy, the local group, and galaxy clusters. Our journey to count the stars of the universe now takes us beyond the comforting familiarity of our own Milky Way, into the vast intergalactic medium where other galaxies, each a star-filled island universe, beckon. Our closest large galactic neighbor is the Andromeda Galaxy, also known as Messier 31. It's an awe-inspiring spiral galaxy, even larger than the Milky Way, located about 2.5 million light-years away. When you look at Andromeda on a clear, dark night, it appears as a faint, fuzzy patch, the most distant object visible to the naked eye. The light you're seeing began its journey 2.5 million years ago, long before modern humans even existed. Andromeda is truly immense. Current estimates suggest that it contains approximately 1 trillion stars. That's a staggering number, roughly 2 to 10 times the number of stars in our own Milky Way. Imagine 1,000 billion suns, each potentially with its own planetary system, all bound together by gravity in one colossal spiral. Andromeda is not just a neighbor, it's a future cosmic dance partner. Our two galaxies are currently hurtling towards each other at a speed of about 110 kilometers per second. In about 4.5 billion years, the Milky Way and Andromeda will collide and merge, forming a new, larger elliptical galaxy that some astronomers have playfully dubbed Milkomeda. This collision won't involve stars actually hitting each other, as the distances between stars are so vast. Instead, the galaxies will pass through each other multiple times, their gravitational fields intermingling and reshaping both structures, eventually settling into a single, grander form. The Milky Way and Andromeda are the two dominant members of what astronomers call the local group. This is our small cosmic neighborhood, a gravitationally bound collection of over 50 galaxies. Besides the Milky Way and Andromeda, the third largest member of the local group is the triangulum galaxy Messier 33, a smaller spiral galaxy with an estimated 40 billion stars. The rest of the local group consists of numerous dwarf galaxies, which are much smaller and contain far fewer stars, often only a few million or a few hundred million. Many of these dwarf galaxies are satellites of the Milky Way or Andromeda, orbiting their larger companions like moons around a planet. The Large Magellanic Cloud and Small Magellanic Cloud, visible from the southern hemisphere, are two prominent dwarf galaxies orbiting the Milky Way. If we sum the stars from all the known galaxies in the local group, the total number easily runs into the trillions. The sheer density of stars in this relatively small region of space, dominated by two massive spirals, gives us a glimpse of the universe's abundance. But the local group is just one tiny speck in the grander cosmic architecture. Galaxies are not randomly scattered throughout the universe. Instead, they are organized into larger structures. The local group itself is part of an even larger structure called the Virgo supercluster, a massive collection of thousands of galaxies, spanning about 110 million light-years across. The Virgo supercluster, in turn, is just one component of an even larger, recently identified structure called Laniakea, which means immense heaven in Hawaiian. Laniakea is a supercluster containing about 100,000 galaxies, stretching over 500 million light-years. Within these superclusters, galaxies are clustered together, forming dense nodes and filaments. Like a vast cosmic web, imagine a sponge, where the material of the sponge represents the galaxy clusters and superclusters, and the empty spaces within the sponge are the cosmic voids. These voids are vast, nearly empty regions of space that can be hundreds of millions of light-years across, containing very few galaxies, if any. They are the inverse of the galaxy filaments, representing the largest structures in the universe. The existence of these intricate structures, from individual galaxies to superclusters and voids, is a direct consequence of gravity acting on matter over billions of years, slowly pulling galaxies together into these colossal cosmic cities. Each galaxy within these clusters and superclusters, whether it's a massive spiral like Andromeda, a majestic elliptical galaxy which can contain even more stars, up to 10 trillion in the largest ones, or a tiny dwarf irregular galaxy, is a universe of stars in itself. The number of stars in even a single dwarf galaxy, while small compared to the Milky Way, still dwarfs the number of stars visible to the naked eye from Earth. As we expand our scope from our local galactic group to the vast tapestry of galaxy clusters and superclusters, the numbers of stars multiply with dizzying speed, preparing us for the ultimate count across the observable universe. The observable universe, reaching the cosmic horizon now. We arrive at the grandest scale we can possibly comprehend, the observable universe. This is not just a theoretical concept, it's a very real boundary, a cosmic horizon beyond which we cannot see, not because our telescopes aren't powerful enough, but because the light from those regions simply hasn't had enough time to reach us. Since the Big Bang, the universe began approximately 13.8 billion years ago. Since light travels at a finite speed, we can only see objects whose light has had 13.8 billion years to reach us. However, the observable universe is much larger than 13.8 billion light-years in radius. This is because the universe has been expanding continuously while the light was traveling. As space itself stretches, distant objects are carried further away, meaning the light we see today from a galaxy that emitted its light 13 billion years ago has traveled a much greater distance than 13 billion light-years. Taking into account this expansion, the observable universe is estimated to be approximately 46.5 billion light-years in radius, making it about 93 billion light-years across. This immense sphere of space contains everything we can, in principle, ever hope to observe. Within this unfathomable volume, how many galaxies are there? This is the crucial question for our star count. For a long time, astronomers estimated that the observable universe contained around 200 billion galaxies. This estimate was largely based on observations from the Hubble Space Telescope, particularly the iconic Hubble Deep Field and Ultra Deep Field images. These images, created by pointing the telescope at seemingly empty patches of sky for hundreds of hours, revealed thousands of galaxies in a tiny, pinprick-sized region. By extrapolating from these small samples to the entire sky, astronomers arrived at the 200 billion figure. However, more recent research, particularly a study published in 2016 that reanalyzed Hubble data and took into account galaxies too faint or too distant to be seen with current technology, revised this estimate significantly upwards. It suggested that there are likely at least 10 times more galaxies than previously thought. The current best estimate for the number of galaxies in the observable universe is approximately 2 trillion galaxies. That's 2,000 billion galaxies, each one a colossal collection of stars. This revision was a monumental shift in our understanding, revealing an even more abundant cosmos than we had dared to imagine. To arrive at the total number of stars, we need to multiply this number of galaxies by the average number of stars per galaxy. This is where the complexities multiply. Galaxies come in a wide range of sizes and types, from tiny dwarf galaxies with a few million stars to giant elliptical galaxies with 10 trillion stars. Our Milky Way, with its 100 billion to 400 billion stars, is a medium-sized galaxy. Andromeda, with its 1 trillion stars, is on the larger side. The average number of stars per galaxy is therefore a complex calculation, requiring astronomers to account for the distribution of galaxy types, e.g., Dwarf galaxies are far more common than massive spirals or ellipticals, but contain fewer stars. Based on various studies and models, a commonly cited average for the number of stars in a typical galaxy is around 100 billion. This is a simplification, but it provides a useful working figure for our grand calculation. So, let's do the math. If there are approximately 2 trillion galaxies in the observable universe, and each galaxy contains, on average, 100 billion stars, the total number of stars is 2 trillion galaxies to trillion, multiplied by 100 million. 0 stars per galaxy, 100 billion. This gives us a mind-boggling total of 200 stars. That's 200 billion trillion stars, or, written in scientific notation, to by 1023 stars. This number is almost impossible to visualize. To try and put it into some perspective, recall our earlier discussion of a trillion. Counting to a trillion, one number per second, would take 31,700 years. Now imagine multiplying that by 200 billion. It's a number that utterly dwarfs anything we encounter in our daily lives. If every grain of sand on every beach on Earth were a star, you'd still be orders of magnitude short of the actual number of stars in the observable universe. If every single living cell in every human body on Earth were a star, you'd still be far, far short. This number represents a truly incomprehensible abundance, a cosmos teeming with luminous points of creation. It's a number that makes us feel incredibly small, yet also incredibly privileged to be able to even conceive of such a vastness. The observable universe, our cosmic home, is not just large, it is overflowing with stars. The unobservable universe and beyond. Limits of knowledge. Our calculation of 200 billion trillion stars refers specifically to the observable universe, the portion of the cosmos from which light has had time to reach us. But what lies beyond this cosmic horizon? This question leads us into the realm of profound speculation and the limits of our current scientific understanding. Is the universe finite or infinite? The answer to this question has direct implications for the total number of stars that might exist, not just within our observable bubble, but in the universe as a whole. Current cosmological models, based on observations of the cosmic microwave background radiation, the afterglow of the Big Bang, and the distribution of galaxies, suggest that the universe is spatially flat. A flat universe, if it extends indefinitely, would be infinite in extent. This is a crucial distinction. If the universe is truly infinite, then the number of stars within it would also be infinite. It would contain an infinite number of galaxies, an infinite number of galaxy clusters, and an infinite number of stars. This concept of infinity is something our brains are truly ill-equipped to handle. It means that every possible arrangement of matter, every possible scenario, every possible history, would not just exist, but would exist an infinite number of times. However, it's important to remember that, while our current observations are consistent with a flat and potentially infinite universe, we can only directly observe a finite portion of it. We don't have enough data to definitively say whether the universe is truly infinite or merely very, very large and extends beyond our observable horizon. It could be that the universe is finite but so vast that its curvature is undetectable within the observable region, much like the surface of the Earth appears flat to us. Even though it's a sphere, the unobservable universe is the portion of the cosmos that exists beyond our cosmic horizon. We know it's there because the universe is larger than the region from which light has had time to reach us. The Big Bang didn't happen at a single point in space, it happened everywhere simultaneously. So, there are regions of space that are simply too far away for their light to have reached us in 13.8 billion years. Even accounting for the expansion of space, we can infer properties of the unobservable universe based on the homogeneity and isotropy of the observable universe, the fact that it appears roughly the same in all directions and at all scales. If the observable universe is a representative sample, then the unobservable universe likely contains similar structures: galaxies, clusters, and, of course, stars in similar densities. If the universe is indeed infinite, then the total number of stars is not just 200 billion trillion, but infinity. This isn't a number we can count or even approximate. It's a concept that challenges our very notions of quantity and existence. In an infinite universe, every star we can imagine, and every star we count, would exist. Some theoretical models go even further, proposing the existence of a multiverse. Multiverse theories suggest that our universe is just one of many, perhaps an infinite number of universes, each with its own set of physical laws, constants, and initial conditions. If the multiverse exists, then the concept of stars in the universe becomes even more complex, encompassing stars in countless other realities. However, it's crucial to label multiverse theories as highly speculative. While some arise from well-established physics, like string theory or inflationary cosmology, there is currently no observational evidence to support their existence. They remain fascinating theoretical constructs, pushing the boundaries of what we can imagine, but firmly outside the realm of verified facts. For the purpose of our question, how many stars exist in the universe, we generally restrict ourselves to the observable universe, as that is the only part we can directly study and quantify. The 200 billion trillion stars is therefore the most accurate, scientifically derived answer we can provide, given our current capabilities. The possibility of an infinite universe beyond our sight, or even a multiverse, adds layers of philosophical depth to the question. But it also highlights the fundamental limits of our knowledge. We are bounded by the speed of light and the age of the universe, creating a cosmic horizon that, for now, defines the extent of our empirical senses. What lies beyond remains a profound mystery, a testament to the fact that even with our incredible scientific advancements, the universe still holds secrets that may forever be beyond our grasp. Why such an enormous number? Cosmic abundance unprocesses the number is truly astounding. 200 billion trillion stars in the observable universe. It's a figure that prompts a natural question. Why? Why is there such an overwhelming abundance of these luminous cosmic furnaces? The answer lies in the fundamental laws of physics, the cosmic ingredients available, and the relentless, efficient processes of star formation that have been unfolding for nearly 13.8 billion years. Since the Big Bang, the cosmic recipe for stars is remarkably simple at its core: hydrogen, helium, and gravity. These were the primary ingredients available in the early universe. The Big Bang produced vast quantities of hydrogen, about 75%, and helium, about 25%, with only trace amounts of lithium. These are the lightest elements, and they are the fuel for stars. Gravity, the universal attractive force, is the sculptor. Wherever matter exists, gravity exerts its pull, drawing particles together. Stars are born in what astronomers call stellar nurseries, giant molecular clouds. These are vast, cold, and dense clouds of gas and dust, often spanning hundreds of light-years across, found primarily within the spiral arms of galaxies. Within these clouds, slight overdensities of matter begin to collapse under their own gravity. As these clumps grow larger, their gravitational pull increases, drawing in more and more material. The collapsing cloud fragments into smaller, denser cores, each destined to become a star. As a core collapses, the pressure and temperature at its center dramatically increase. Eventually, the core becomes hot and dense enough for nuclear fusion to ignite. This is the moment a protostar becomes a true star, joining the main sequence. Hydrogen atoms in its core begin to fuse into helium, releasing an enormous amount of energy in the process. This outward pressure from fusion balances the inward pull of gravity, stabilizing the star and allowing it to shine for millions, billions, or even trillions of years. This process of star formation is not a rare event, it's a continuous, ongoing cycle throughout galaxies. The rate of star formation has not been constant throughout cosmic history. Observations of distant galaxies, which we see as they were billions of years ago due to the finite speed of light, indicate that the universe experienced a peak in star formation about 10 billion years ago, roughly 3.8 billion years after the Big Bang. During this cosmic noon, stars were forming at a much higher rate than they are today. Galaxies were more active, often colliding and merging, which triggered bursts of intense star formation. Since then, the overall star formation rate has gradually declined, as the available gas and dust in galaxies have been used up or locked away in existing stars and stellar remnants. However, star formation continues even today in galaxies like our Milky Way, albeit at a slower pace. The life cycle of stars also contributes to the sheer number. Stars have vastly different lifespans depending on their mass. Massive stars burn their fuel quickly and live for only a few million years, ending their lives in spectacular supernova explosions. These explosions are crucial for enriching the universe with heavier elements, such as carbon, oxygen, iron, and all the elements essential for planets and life. Smaller stars, like red dwarfs, are incredibly long-lived, potentially shining for trillions of years. Our Sun, a medium-sized star, will live for about 10 billion years in its main sequence phase, having already completed about 4.6 billion years of that journey. This diversity in stellar lifespans means that the universe is populated by stars at all stages of their evolution. There are young, hot, blue stars just born stable, middle-aged stars like our Sun, expanding red giants, and the dense remnants of dead stars, white dwarfs, neutron stars, and black holes. All of these contribute to the stellar census, even if some no longer actively fuse hydrogen. Crucially, the universe is a master of recycling. When massive stars explode as supernovae, or when smaller stars gently shed their outer layers to form planetary nebulae, they release their enriched material back into the interstellar medium. This material, now containing heavier elements forged in the star's cores, mixes with the remaining hydrogen and helium. These enriched clouds then become the raw material for new generations of stars and planets. This stellar recycling ensures that the ingredients for star formation are continually replenished and diversified, allowing new stars to form throughout galactic history. Without this recycling, star formation would have ceased long ago. In essence, stars are the universe's primary light bulbs and element factories. They are the fundamental units that convert primordial hydrogen and helium into the diverse array of elements that make up everything we see, from rocks and water to complex organic molecules and living beings. The sheer number of stars, therefore, is a testament to the universe's capacity for creation, its inherent drive to organize matter into luminous, energy-producing structures. It reflects the immense quantities of hydrogen and helium available, the pervasive influence of gravity, and the efficient, self-sustaining cycle of stellar birth, life, and death that has been underway for billions of years. The universe is not just vast, it is incredibly fertile, constantly giving birth to new suns in numbers that defy our most ambitious attempts at counting. The significance of the count, philosophical and practical implications. The existence of 200 billion trillion stars in the observable universe is not merely a colossal number, it carries profound philosophical and practical implications that reverberate through our understanding of our place in the cosmos, the search for life, and the long-term future of humanity. Philosophically, this immense count is deeply humbling. It places our Earth, our Sun, and indeed our entire Milky Way galaxy into a perspective of almost unimaginable insignificance. We are a small planet orbiting an ordinary star, in one of hundreds of billions of galaxies, within a universe teeming with trillions upon trillions of suns. The entire history of human civilization, every triumph and tragedy, every great work of art, every scientific discovery, every war fought and peace brokered, has occurred on this single, tiny world. From a cosmic viewpoint, our existence is a brief flicker, our planet a speck of dust, and our concerns often seem trivial in the face of such vastness. This isn't meant to diminish the importance of human life or our individual experiences. but rather to provide a profound sense of scale. When we contemplate the sheer number of stars, our personal problems, our daily anxieties, our worldly squabbles, can sometimes feel less overwhelming, placed against a backdrop of such immense, indifferent cosmic majesty. The abundance of stars also fuels one of humanity's most enduring questions. Are we alone? The sheer statistical probability, given 200 billion trillion stars, and the knowledge that most stars host planets, strongly suggests that life should exist elsewhere. If even a tiny fraction of these stars have planets in habitable zones, regions where temperatures could allow liquid water, and if life can arise relatively easily given the right conditions, as it seems to have done quickly on Earth, then the universe should be teeming with life. This leads directly to the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody? If life is so common, why have we found no evidence of other intelligent, technological civilizations?" The vast distances measured in light years, as we've discussed, are a major part of the potential answer. Even if civilizations are abundant, the sheer scale of interstellar space and the finite speed of light make communication and travel incredibly difficult, potentially impossible for practical purposes. A civilization might be just a few hundred or a few thousand light years away, but the time delays for communication would span centuries or millennia, making any real-time dialogue impossible. We might be like ships passing in the night, separated by cosmic oceans to vast across or even signal effectively. The number of stars suggests life should be out there, but the distances between them might ensure our isolation. From a practical standpoint, the vast number of stars points to an almost limitless reservoir of energy and resources. For a future humanity that might seek to expand beyond Earth, other stars offer potential new homes, new sources of energy, and new materials. The concept of stellar mining, extracting valuable elements from stars or their surrounding nebulae, remains firmly in the realm of science fiction, but the sheer abundance of stellar material is undeniable. Each star is a massive fusion reactor, churning out energy for billions of years. If humanity ever masters interstellar travel or obtains access to the energy of even a few stars, our resource constraints would be fundamentally altered. Furthermore, the knowledge that we are made of stardust connects us intimately to this cosmic abundance. The hydrogen and helium in our bodies originated in the Big Bang, but all the heavier elements, the carbon, oxygen, nitrogen, iron, and countless others that make up our planet and our bodies, were forged in the hearts of stars and scattered across space in supernova explosions. We are literally the recycled material of ancient, long-dead stars. Every atom in your hand, every breath you take, every thought you think, traces its origin back to a stellar furnace. This realization is not just poetic, it's a scientific truth that binds us directly to the immense stellar population of the universe. We are not just observing stars, we are intrinsically a part of them. The future of stars, and indeed the universe, is also shaped by this count. Stars are born, live, and die, and this cycle has a finite lifespan. In trillions of years, the last red dwarf stars will slowly fade away, having exhausted their fuel. Galaxies will eventually merge and settle, becoming vast, cold collections of stellar remnants. The universe itself, as it continues to expand and cool due to dark energy, is heading towards a heat death, a state of maximum entropy where all energy is evenly distributed and no further work or processes can occur. In this unimaginably distant future, the 200 billion trillion stars we count today will largely be gone, replaced by black holes, neutron stars, and white dwarfs, slowly cooling into black dwarfs. The universe will become a dark, silent, and empty place. Our current era, teeming with luminous stars, is a temporary, vibrant phase in the universe's long history. Understanding the number of stars, therefore, is not just an exercise in cosmic accounting, it's a journey into our past, a reflection on our present, and a contemplation of our ultimate future. It forces us to confront the deepest questions about existence, purpose, and our place in a universe that is both overwhelmingly vast and intimately connected to our very being. The sheer abundance of stars is a testament to the universe's creative power, and our ability to count them, even approximately, is a testament to the power of the human mind. Conclusion: a universe of stars tonight. We've embarked on an extraordinary journey, moving from the familiar comforts of our own night sky to the unimaginable depths of the observable universe. We began by acknowledging the humble number of stars visible to the naked eye, a mere handful of thousands, and quickly realized that this terrestrial perspective offers only the faintest glimpse of the true cosmic abundance. We zoomed in on our sun, an ordinary star, and its immediate neighbors, learning that even the closest stars are separated by light years, vast stretches of empty space that emphasize the sparse distribution of luminous bodies. This led us to our galactic home, the Milky Way, a magnificent barred spiral galaxy estimated to contain between 100 billion and 400 billion stars. We explored the ingenious methods astronomers use to count these stars, peering through dust and extrapolating from galactic dynamics. Our journey then took us beyond our galaxy to the local group, dominated by the Milky Way and the colossal Andromeda galaxy, which alone harbors an estimated 1 trillion stars. We saw how galaxies cluster into superclusters, forming a vast cosmic web, with immense voids separating these grand structures. Finally, we reached the cosmic horizon, the limit of what we can possibly observe, the observable universe. Within this immense sphere, spanning 93 billion light-years across, our best estimates tell us there are approximately 2 trillion galaxies, and when we multiply that astounding number by the average number of stars per galaxy, we arrive at our grand total, 200 billion trillion stars. That's a 2 followed by 23 zeros. This number is not merely large, it's profoundly, almost incomprehensibly vast. It represents an abundance that dwarfs any human scale or experience. When you look up at the night sky, remember that every point of light you see is a star. But also remember that for every visible star, there are billions upon billions more that remain hidden from the naked eye, silently burning in the depths of space. You are literally looking into the past, seeing light that has traveled for years, centuries, or even millennia to reach your eyes. The light from distant galaxies began its journey billions of years ago, before our solar system even formed, offering us a glimpse of the universe as it was in its infancy. This count of stars is not a final, immutable figure. As our technology improves, as new telescopes like the James Webb Space Telescope peer even deeper into the cosmos, and as our understanding of astrophysics evolves, these numbers may be refined. We might discover even more faint, distant galaxies, pushing the total higher. The universe remains a place of ongoing discovery, constantly revealing new layers of complexity and abundance. The wonder and mystery that remain are as vast as the number of stars themselves. We still don't fully understand dark energy, the mysterious force accelerating the universe's expansion. We still grapple with the nature of dark matter, the invisible scaffolding that holds galaxies together, and the profound question of life beyond Earth, of whether any of those 200 billion trillion stars host other intelligent civilizations, continues to fuel our curiosity and our scientific endeavors. So, the next time you look up at the night sky, take a moment to truly contemplate what you are seeing and what you are not seeing. Those scattered points of light are not just beautiful, they are a gateway to understanding the true scale of the universe. A testament to the unimaginable number of suns that exist within our observable cosmos. You are a conscious being, made of stardust, capable of comprehending this astonishing reality. That ability, that wonder, that thirst for knowledge, is what makes us truly unique in this vast, star-filled universe. Thank you for joining me on this journey through space and time. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the cosmos. And remember, the universe, vast as it is is yours to explore, one star, one galaxy, one cosmic mystery at a time. Good night, and may you never look at the stars the same way again.